Welcome back, everybody. This is going to be the final of 3 parts in my lecture series on compositions of functions. If you haven't seen the first 2 parts, please go and watch them now, as they're going to be important for this part. In this video, we're going to look at how to write down compositions of functions using function notation. Let's get started. Let's suppose that I have 2 functions f and g. Their composition is f of g of x. That's how I read both sides of this. F of g of x. Provided that g of x is in the domain of f. Essentially, a composition is where I take one function and plug it in as an input for another one. Let's take a look at an example. Let's suppose that f of x is 5 over x plus 4, and g of x is the square root of 1 minus x. Let's compose each of the following and then find their domains. For part A, we're being asked to find f of g of x. Now, I've never personally been a big fan of this notation. I prefer to write it as literally f of g of x. Now, this is saying that I want to take g of x and plug it in as an input to f of x. So, everywhere I see an x in my f of x, instead I'm going to write a square root of 1 minus x. This gives me 5 over input plus 4. 5 over input plus 4. So, now let's find the domain. I've got all sorts of stuff going on in this one. I've got a 1 minus x under a radical. Or I should say under an even radical. Now, I know this guy has to be greater than or equal to 0. Solving for x, I would add the x over to both sides and get that x has to be less than or equal to 1. Cool. Alternatively, though, I've got that the square root of 1 minus x plus 4 is in a denominator. So I know that that guy cannot be equal to 0. Solving for x, I would move the 4 over to the other side. I would square both sides. I would subtract the 1 and divide by -1 to get that x cannot be -15. So, all numbers less than or equal to 1 that aren't -15 fit. That tells me the domain is -infinity up to -15, excluding it, and -15 up to 1, including it, to be the domain of this problem. In the next problem, notice this is subtly different. I've got f, instead of f of g of x, I have g of f of x. So this time I'm taking f of x and plugging it in to be the input for g of x. For this problem, we're actually going to need to use a new tool called a sign chart. Because when I plug in f of x into g, I get the square root of 1 minus input, which happens to be 5 over 4 plus x. Or x plus 4, I guess. Now, I like to fully simplify if I can. The way to do that here is get a common denominator, and I'll write that as x plus 4 over x plus 4, minus 5 over x plus 4. And now I can just subtract them. And in the numerator, I get x minus 1. In the denominator, I get x plus 4. Now here's the deal. It can be a little bit tricky to tell what the sign of the thing under the radical is, because I know I need x minus 1 over x plus 4 to be greater than or equal to 0. Right? I know that this is what I need, but the value of x changes this dramatically. So a sign chart is a tool that's going to help us break it down. And I'm going to give myself a little bit more room here. So, how do I use a sign chart? Well, first, I need to find the zeros of the numerator and denominator. Here, in a little thought bubble here, the numerator, x minus 1, is going to be 0 if x is 1. And the denominator here, x plus 4, is going to be 0 when x is negative 4. The reason why this is important information is because to the left and right of these zeros is where the function is going to be changing sign. Think about it as crossing the x-axis. That's when y equals 0, right? So it's going to change from being above the x-axis to below the x-axis. So now what I do is I plot a number line with those zeros on it. I need to plot it with negative 4 and 1. And what I know is the function is only going to change sign at these zeros, potentially. So all I need to do is just check something on each piece of the number line to see what the sign is. For example, if I check, I guess it would be more over here, at 0, when I plug in 0, I get 0 minus 1 over 0 plus 4, which is going to give me negative 1/4. That's a negative number. So I know in this whole region, it's negative. Now I need to pick a number on the left side. Let's try negative 5. Here, I'll get negative 5 minus 1 over negative 5 plus 4. That's going to be negative 6 over negative 1, or 6, which is positive. So over here, I'm positive. Similarly, I just need to check a point over here. Let's try 2. I'll get 2 minus 1 over 2 plus 4 is 1/6, which is positive. So positive over here. Now, why did I go through all this trouble? Because this is the guy under the radical, and I need to make sure it's greater than or equal to 0. That's going to happen in this region on the left and this region on the right. So, one part of my domain here is going to be that x has to be less than or equal to negative 4, and x has to be greater than or equal to 1. Excuse me. Has to be less than negative 4. It can't be negative 4 because that would cause division by 0 in the denominator. So the only other thing to consider is exactly what I just pointed out, that x plus 4 can't be 0, so I can't actually have negative 4. Altogether, the domain, would be negative infinity up to negative 4, excluding it, together with 1 to infinity, including the 1. Now, it's going to be helpful for math classes beyond this one, namely in Calculus 1. If you have to take Calculus 1, you will need to know this information. To find non-trivial decompositions, that's the super fancy name, right? Essentially, what I'm asking you to do in each of these parts is to look at this function and break it up into a composition of functions. And I think it'll be a little bit more clear if we do part A together. What I see here is that I've got this polynomial, 2x minus 5. So let me call that guy g of x. G of x is 2x minus 5. And that whole thing is being raised to the 4th power. So it almost looks like I've got a 4th power in there too, x to the 4th. And I can rewrite this function as f of g of x. Now, what does the word non-trivial here mean? Well, I could do something cheap, right? I could take a cheap shot at this problem. And the trivial way, I'm going to write it in gray, would be to just say g of x is just x, and then f of x is everything else. Because I'm just plugging x into f as I've written it here, but that's kind of a cheap shot, right? That's not what we're looking for in this problem. Go ahead and pause the video here to see if you can do part B on your own. An answer that I found was to let g of x be 5x to the fourth plus 1, and f of x to be the cubed root of x. But with these problems, there are usually multiple correct answers. For example, you may also have said that g of x was 5x to the fourth, and that f of x was the cubed root of x plus 1. That would also be a valid answer for this problem. In this video, we looked at how to compose and decompose functions, and we looked at what happens to their domains when we do that. That's going to wrap it up for this series. Catch y'all in the next one.